Hey guys, welcome to your Chapter 17 Part 2 video. We're going to do three things here today. We're going to show you calculator functions for the geometric model, for the binomial model, and then I'm going to show you a normal distribution approximation to the binomial model, which sounds like it's really complex. Thankfully, it really isn't, and it simplifies a lot of problems whenever the number of trials you would have for your binomial model becomes big. Like if you've got 50 trials in all, and you want to know what's the likelihood that you have 25 or fewer, or well, maybe that's not an interesting question, but maybe 30 or fewer, something like that, the normal distribution will work just fine. You'll see more on that here in just a bit. Okay, so first of all, let's approach a problem that we've seen before. You flipped a loaded coin. The probability of a head being flipped is 0.40, while the probability of a tail being flipped is 0.60. We want the probability that the first head to be flipped occurs on the fourth flip of the coin. Okay, well, let's first of all identify if there's a model that we've seen from Chapter 17. Oh, excuse me. Oh, let's see if there's a model that would work in this case. So let's identify whether or not we have Bernoulli trials. Okay, do we have two outcomes per flip of the coin? Sure, head or tails. Do we have independent events? Sure, even though it's loaded, one flip of the coin should not affect the next flip of the coin, so we have independence. And they're telling us this constant probability of success. Depends upon how you define success. Success could be flipping a head, success could be flipping a tail, but regardless, both are constant, so you do have Bernoulli trials. Okay, so let's define the random variable x to be the number of flips until, excuse me, the sinuses are acting up today. So first head seed. Okay, so we want the probability that x is equal to 4, which we could do without a calculator just by saying, okay, well, to see the first success on the fourth flip, that would be 3 failures followed by your single success. Okay, you can work with that simply. But let's go to Wabbit, which we've not worked with in a little while. And let me make sure this guy's working okay. On. Let me reopen him. What's going on? Okay, there we go. Oh, RAM cleared. Let me think if that's going to affect what we're doing at all. I don't think it should. Okay, so I'm going to go to second distribution, and I'll scroll up to go to the bottom of the list, and there is Geomet PDF and a Geomet CDF. We're going to use both in this slide, and I'll explain the difference as we go. Geomet PDF finds the probability that you would have your first successful trial on your xth trial. Okay, so I'm going to click on that because that's what we want right now. We want to find the probability that our first successful trial is on our fourth trial here. So we'll hit enter, and they ask for, okay, this is not how every calculator is going to look. They're asking for a p-value, the probability of success. Well, the probability of success, if that's heads, is 0.40, and the x value then is 4. And I don't know why this is paste rather than enter. I have no idea why they call it that. And we'll hit enter again, and we find the probability that your first head at a 40% likelihood per flip is going to be 0.80864. Okay, some of your calculators are going to display that differently. Some of you guys will have to do the following. When you hit Geomet PDF from second distribution, it'll bring up the following: Geomet PDF, open parentheses, and then you'll need to enter the following. You would say probability of success first, which is 0.40, and then the xth case you want to see your first success on, so 4, and that would give you the same 8 point whatever percent, 8.64. Okay. All right, so there's Geomet PDF. Now let's look at Geomet CDF. What is the probability that the first head to be flipped occurs on the first, second, or third flip of the coin? Okay, so this time we're answering the question of x, the probability that x equals 1, plus the probability that x equals 2, plus the probability that x equals 3, which we can say is just, using Geomet CDF, the following. Second distribution, I'll scroll up again to get to the bottom of the list. It's the very bottom there. P-value is the same, 0.40, because we're still talking about a head flip. X value I'm going to enter to be 3. That's the most successes we were looking for, I believe, yeah, in part B, 3. And then paste, enter, 0.784, so a 74% chance. So what Geomet PDF did in part A is it found the probability of success on a single trial. Geomet CDF, if I say the following, Geomet CDF, where the probability of success is at 0.40, and I enter trial number 3, that's going to give me everything right here that I'm underlining. The probability that you see your first success on the first trial, the second trial, or the third trial. So if, for instance, in a different color here, let's deviate from the problem just a little bit. If I enter in Geomet CDF, let's go with the same probability of success for a head, 0.40, comma 7, that's going to give me the probability that you see your first success on the first trial, plus the probability that you see your first success, not with the plus sign, with an equal sign, on your second trial, onwards and onwards, up to the probability that you'd see your first success on your sixth trial, up to your seventh. Okay? So Geomet CDF finds the probability of success for that xth number of trials or fewer. All right, so let's see how we can use this one more time. Use Geomet CDF in part C. What's the probability that the first head to be flipped occurs on or after the fifth flip of the coin? Okay, so they want us to answer this following question. Once again, if x is following a geometric model, where we're looking for the first success on whatever trial, they want us to find the probability that x is equal to 5, first success on the fifth trial, plus the sixth, plus onwards and onwards, just forever. Well, why don't we use the idea of a complement? What's the opposite of a first success occurring on the fifth, sixth, seventh, etc., up to the infinite trial? Well, that would be equal to 1 minus the probability that it occur on your first trial plus your second. What's going on with my writing today? Plus your third plus your fourth. Okay? That becomes a simpler problem to solve rather than trying to find an infinite number of disjoint probabilities. Let's just work with the 4 probabilities that we clearly are not talking about. Okay? So we can, instead of using Geomet PDF here, Geomet PDF here, Geomet PDF here, Geomet PDF here to find those 4 individual probabilities, why don't we, for everything in the bracket, just use Geomet CDF instead? So we'll say 1 minus Geomet CDF of, again, that 40% probability of success, comma 4. And that gives us, using Wabbit, 1 minus second distribution, scroll up, Geomet CDF will enter in 4, paste. Let me make sure that the syntax is good. Yeah, and that looks correct. We'll hit enter there. Okay, so we find a 12.96% chance that your first head success will occur on the 5th, 6th, or etc., trial. That is flip of the coin. Okay. All right. So 2 calculator functions that will save a lot of time for you as you go through these geometric and binomial model problems. You're welcome to use them whenever you feel like they're applicable. What I want you to do if you use these models, or really calculator functions, if you use these calculator functions, you need to tell me the following things going into the problem so I can trace what you're doing for partial credit purposes. You need to tell me the probability of success that you're using. In this case, it was 0.40. You need to tell me the x value you're using for your calculator. So for this last problem, we used x equals 4 when we were using the complement. Anytime you use some sort of an equation to simplify, I'm only circling the right side, but anytime you attack the problem indirectly, try to write something out for me that represents how you're solving the problem. For many of you guys, it's way too time consuming to try to follow how you may have solved a problem case by case unless you're writing stuff out. So at the bare minimum, give me the probability of success, give me the number of trials you're entering in, tell me if you're using Geomet CDF or Geomet PDF. That will tell me whether or not you're using the correct function at the right time. Okay, that sort of stuff. Don't just enter this in and put the answer down on paper. All right, second thing here. Suppose you really care to collect Tiger Woods boxes of Wheaties cereal. However, I don't even know if he'd be endorsed by Wheaties at this point with that infidelity fiasco with his wife. Sheesh. Anyway, however, Tiger Woods is one of many sponsors of the boxes of cereal, and his celebrity photo is only on 20% of the Wheaties cereal boxes. Okay, so there's your probability of success, 20%. If you buy 20 boxes of Wheaties, what's the probability that you find his photo on 6 of the boxes? Okay, well, once again, let's identify whether or not we have Bernoulli trials. Okay, we have 2 outcomes. Tiger Woods box or not a Tiger Woods box, so that's a go. You've got a constant probability of success at 20%, and if they're telling you 20% of the boxes coming off of the assembly line are Tiger Woods boxes, then you've got a constant probability of success, because really it's a random event here where one box should not affect the outcome of the next box. Okay. All right, so Bernoulli trials are a go. We'll define x to be, or really let's switch it up. We don't always have to use x for a random variable. We'll define y to be the number of Tiger Woods boxes in 20 boxes bought. Okay. What's the probability that you find his photo in 6 of the boxes? So they want us to answer the question that the probability of y equals 6. Well, we can do that, again, using your calculator with another function that's in second distribution. Same place you go for normal CDF, rather, an inverse norm. We'll go up to the binomial PDF. They ask for the number of trials here. I need to sneeze again. Excuse me. The number of trials, which we'll enter to be 20. The probability of success is 0.20 this time around, and they wanted 6 successes, so we'll enter that. We'll paste this and enter this in, and there's a 10.9% chance that you see 6 Tiger Woods boxes out of 20 boxes in all. Okay? All right, so some of you, just as before, may not see binom PDF appear quite this way. For some of you guys, when you enter in binom PDF, it'll take you back to the home screen and you'll just see this. Well, you need to enter in 3 arguments or 3 numbers here. The first is the number of trials, which is 20. The second is the probability of success, which is 0.20. And then x is the number of successes you're looking for. So 6 in this case, and that'll take you to the same 10.9% chance that we just found using this other look on the calculator. Okay. All right, so there's part A. Now on to part B. They say, if you buy 20 boxes of Wheaties, what's the probability that you find his photo on 7 or fewer of the boxes? Well, aha! Last slide, we had this CDF thing that found the probability of success on the xth trial or less, down to 1. Binom CDF is actually going to do the same thing. In the 20 cases, the 20 boxes of Wheaties that you buy, it's going to give you the probability of 7 or fewer successes. Okay, so here we're finding the probability that y is less than or equal to 7, which breaks down as the probability that y equals 1, plus the probability that y equals 2, plus the probability that y equals 3, up to 7. So we can just do binomial CDF instead of PDF. The C in CDF stands for cumulative density function, which the reason they don't really spell that out for you is because that comes from an integral. If you guys go on to take calculus-based probability and statistics, some of you will integrate a continuous curve to find a probability of success from a density function. And so just think of the C as the accumulation of multiple successes. We want 1, 2, 3, 4, 5, 6, or 7. Okay? So C is for groups, P is for a single person, a single case. Okay, so let's enter in binomial CDF and see what happens. We have second distribution. We'll scroll up to binomial CDF. Trials is 20. Probability of success is 0.20. X value is 7, and that'll find the 7 or fewer successes. We'll enter this in, and they tell us, whoa, that's a lot, 96.8%. So for 20 trials, on that probability of success, we had 96.8% chance of finding 7 or fewer boxes of Tiger Woods Wheaties cereal. Okay. All right. So those calculator functions will help you immensely. Once again, with the binomial PDF or the binomial CDF functions, you need to tell me on any problem that you're using these calculator functions. First of all, the number of trials that you're entering in, the probability of success, the number of successes you're looking for, and I also need to see, at the bare minimum, tell me if you're using PDF or CDF. No, you're not going to get credit on the AP exam for saying that, but I can award partial credit by understanding your logic. I need to understand your logic and how you got to a particular answer. If you were to go about each of these problems in the best possible manner, you would, for both the sake of the AP exam and for a test in here, you would define a random variable, and you would, at a bare minimum, write out the probability that you're trying to find, and then your answer, okay? But for those who are just using a calculator function, I need to see what's being plugged into the calculator, so write that out, please. So same thing here. If you go about this, solving this in the best possible manner, you would define your random variable, you would write out the probability that you're solving, and then you give me your answer like that. For those, again, who are just using the calculator function, let me see the numbers you're plugging in. Okay, so last thing we're going to do here, let's see why we would not want to go about this using the methods we've seen from earlier in Chapter 17. Suppose the Tennessee Red Cross anticipates the need for at least 1,850 units of O-negative blood this year. We'll assume 6% of the population has O-negative. It estimates that it will collect blood from 32,000 donors. How great is the risk that the Tennessee Red Cross will fall short of meeting its need? Okay. Well, first of all, let's talk about whether or not we have Bernoulli trials. We have two outcomes. We either have O-negative blood on a per donor basis, or you don't have O-negative blood per donor. You've got an independent probability of success, assuming these people just come in from at random from the community, and you've got a constant probability of success of 6%. So Bernoulli trials are met. Well, because we're talking about multiple successes out of these 32,000 trials, that's clearly not a case of the geometric model to be used. We're talking about the binomial model here. So if x equals the number of O negative blood units donated out of 32,000 donors, then what they're really wanting us to find, how great is the risk that we don't meet the 1850? That's the probability that we have only one success, only one O negative donor out of 32,000, plus 2, plus onwards and onwards up to 1850. Okay? So holy cow, who wants to evaluate by hand 1,850 different disjoint probabilities? No one. There's an easier way to do this, and this involves a different model to approximate the binomial. Let's go to an Excel file here that I've set up. Oh, excuse me, my sinuses. Sheesh. What I've done in this Excel file, in sheet 1, I'll scroll through and you can see there are 50 different rows on the right-hand side. And what I'm going to show you here is how we get to that normal approximation of the binomial distribution. Well, for each row, what I did, as I said, okay, row 1, that'll be where out of 50 trials in all, I had 0 successes. Row 2 will be where I had 1 success out of 50 trials. Row 3 will be where I had 2 successes out of 50 trials. So we have 50 trials, and the way I've set this up, these are Bernoulli trials, and for each cell, let me show you what I entered. For this first cell here, it's taking A1, which is 0. That's the number of successes. We've got 50 trials, and the probability of success is 20%. So this cell under column C is the probability I would see 0 successes out of those 50 trials in all. Okay? And then we go to the next. Whoa. No. Don't undo. Oh, goodness. Okay. Oh, good Lord. I'm going to reopen this. No, don't save. Excel's so stupid sometimes. Or at least, maybe it's operator error. Sure it is, but still, it frustrates me. I found this. I made this last year. Chapter 17, normal approximation to the binomial. Okay. I'll just not click on any of the cells. Okay. So again, what we did here for this is 0 successes out of 50 trials, where the probability of success is 0.20. Then we go to 1 success out of 50 trials, where the probability of success per trial of the 50 is 20%. That's the probability you'd see just 1 success out of 50 trials and all, etc., etc. Okay? So first of all, I made sure that if you indeed have 50 trials, that all these probabilities add up to 1. And so this is the sum from C1 to C51. That is 0 through 50 successes, and sure enough, it adds up to 100%. So that accounts for all the different ways you could see successes in 50 trials. Well, notice when I make a histogram that has on the horizontal axis the number of successes, and on the vertical axis we have the probability for each of those numbers. Okay? So 0 successes out of 50, when you've got a 20% chance of success per trial, is incredibly low. It's virtually 0. Then you get up closer to 10 to see 10 successes out of 50, where there's a 20% chance of success. Well, that's where this histogram rather is at an all-time high. Well, it looks like I need to erase some of this stuff if I'm going to scroll. Okay, that's where it's at an all-time high. So for 10 successes, you've got essentially, now maybe it doesn't quite hit the line. It's hard to tell when the number of significant digits goes out like 8 units, or 8 digits here. But it looks like a 14% chance, approximately, of having 10 successes out of 50 trials with a 20% probability of success trial by trial. Okay, so clearly what you have going on here is a normal bell curve shape. Okay. Now the only difference, we know the normal bell curve is smooth. Okay. Normal bell curve is smooth, but this is pretty close. Yeah, it's got these jumps from bend to bend, but still you can essentially approximate your binomial model with a normal bell curve here. And the parameters just come from the binomial distribution. The binomial distribution says if x is number of successes out of n trials, then your expected value of x is just n times p, the number of trials times the probability of success. Well, here we had 50 trials. The probability of success was 20%. 20% of 50 is 10, okay? So this normal bell curve has a mean of 10, and the standard deviation from the binomial model is the square root of n times p times q, which would be the square root of 50 times 20% times 80% here. And that I don't know off the top of my head. Let's see, 50, 20, 80, 16, 50, about 0.8. That doesn't sound right, but regardless, you've got a standard deviation that comes from your binomial model. Okay, so let's look at this one more time. Sheet 2 didn't copy. Oh, that's right, because it wasn't saved from when, or whatever. So what I'm going to do here, let's take this same sheet. Let's create a copy in sheet 2. Yeah, okay, and now I'm going to change one thing. I'm going to see if I can do this without gumming everything up. I'm going to change the probability of success for every trial to be 40% instead of 20%. We're still using the cell in column A to be the number of successes out of 50 trials in all. So let's see what changes in my distribution, in my histogram. Okay, so sure enough, Excel's kind of swanky in this sense. I still have 100% of all the cases, all the different ways that you can get n successes out of 50 or x successes out of 50 added up here. Well, the distribution shifted to the right a little bit. From here it was far left, now it's to the right. And that's just because we increased the probability of success. So whereas we said last slide, if we can use a normal approximation to this binomial model, well, if the mean of the normal model here, given this is coming from binomials, n times p, well, now it's 50 times 40%, which is 20, okay? And sure enough, there's the mean of both the histogram and of the bell curve that I'm drawing over the histogram. Standard deviation is still calculated as square root of n times p times q. Okay, so the only condition that has to be met to make sure that you can use a normal bell curve to approximate a binomial distribution is the following two things. Let me erase this because as I scroll down and make room, it's going to follow along. Okay. The only two things, the only two conditions are the following. Okay, you need first greater than or equal to 10 successes, and you need greater than or equal to 10 failures. Okay? Basically, you need a lot of trials to use the binomial model. The binomial model wouldn't be a good tool to use if you had just 6 flips of the coin and you wanted to see the probability that you had 4 heads out of 6 flips of a coin. There's not enough stuff going on to be approximated by the bell curve there. Okay? All right, so those are your conditions. Let's see this in action in an example real quick. Let's go back here to example 3. I'll erase the solution method we would have used prior to knowing about this normal approximation. Oh, and I don't want to erase the fact that it's Bernoulli trials. We still have that. We've already verified the Bernoulli trials are here. Okay, so let's see if we expect to see at least 10 successes and at least 10 failures. Well, we have the number of trials times the probability of success is the number of successes we expect to see. We have 32,000 donors or trials in all times the probability of success of 6%, which takes us to 1,920, which is certainly greater than 10. So the first condition is met. Now for the number of failures, well, that's just if there are 32,000 donors in all and 1,920 of them were successes, we expect to see being successes, then 30,080 of them we expect to see failures, and that's certainly greater than 10. So the number of successes we expect to see and the number of failures we expect to see both exceed 10, so we're good to go with the normal distribution. Okay, so let's draw a normal bell curve here, and this is going to be the distribution of number of O negative blood donors out of 32,000. Okay. Well, again, we said the mean for this normal approximation to the binomial model is just, I did not define a random variable, so x is equal to the number of successes and 32,000 trials. Okay, so the mean is just n times p, which is 32,000. Well, we already found that. I don't need to rewrite that out. That was part of the conditions. We expect to see 1,920 people who have this blood type. That's our expectation. Doesn't mean it's going to be the case. We expect to see that. Standard deviation of x is equal to the square root of NPQ, which is the square root of 32,000 times 6% times 94%, which is 42.48, which interestingly, out of 32,000 donors, that's not a whole lot of variation. I would intuitively expect to see the amount of variability within 68% of the mean, remembering the 68, 95, 99, 7 rule. I would expect to see within one standard deviation of the mean, maybe 100 for a standard deviation, or closer to 1,000, a lot more variation. But as the number of cases, the number of trials grows, it's going to be that much rarer to deviate from the mean. Okay, so one standard deviation away to either side, you've got 1872.52 or 1962.48. Okay, well, our cutoff value, the x value we care about, is 1850. We want to make sure we hit at least that number. So we're over here on the bell curve. They want the probability that we'll fall short of meeting the need. So we don't want the probability greater than this amount. We want the probability less than this amount. Okay, so let's say that the z-score is equal to 1850 minus your mean of 1920, divide through by your standard deviation. That takes you to negative 1.648. Okay, so to wrap this up, we're going to use normal CDF here from negative 1.648 is not my lower, negative 1,000 would be my lower, negative 1.648 is the upper cutoff value. And that gives you, going back to Wabbit real quick, second distribution, normal CDF. Wait a second. Oh, yeah, that works. Okay, so that's really low. Negative 1.648. We'll paste that. Okay, so there's approximately a 5% chance we won't hit our mark. It is 4.97 percent chance. Okay. All right, and there you go. You've seen calculator functions for geometric and binomial models, and you've seen this really handy normal approximation to the binomial distribution, which requires at least 10 successes and at least